Standing before the massive skeleton of a dinosaur, one question almost always arises. How do scientists know this fossil is 70 million years old? Old and not just 7,000? That staggering number, 70 million, feels so distant, almost unimaginable, and naturally sparks skepticism. Are these dating methods truly reliable, or are they merely built on assumptions we rarely hear about? To uncover the answer, we must journey into the world of science, where geology, biology, and physics converge to create a grand clock measuring the passage of Earth's history. The age of a fossil is never a random guess. It is the result of a meticulous process grounded in two main pillars: relative dating and absolute dating. Understanding these methods reveals that fossil dating is far more than a dry physical measurement. It transforms a simple number into a vivid story. By connecting an age to geological and biological evidence, scientists can reconstruct the environment, the ecosystems, and even the ancient landscapes where these creatures once lived. Science does not aim to conceal its assumptions. It exposes them, then develops methods to test and refine them. This process reflects the discipline and self-correcting nature of science, steadily shaping a reliable portrait of Earth's past. Relative dating. Layer by layer, telling ancient stories. Long before absolute dating techniques existed, geologists and paleontologists relied on relative dating to establish the order of past events. This approach does not provide an exact age in years. Instead, it tells us whether something is older or younger compared to something else. At the heart of relative dating lies the law of superposition. This principle states that in an undisturbed sequence of sedimentary rocks, the layers at the bottom are always older than the ones on top because they were deposited first. In simple terms, younger layers bury older ones, much like stacking books. Although geological forces such as faulting or metamorphism can disturb these layers, scientists have developed techniques to recognize and correct these distortions. With this principle, researchers can determine that a fossil found in deeper rock layers is older than one found closer to the surface at the same site. This was a critical breakthrough, allowing scientists to establish a chronological sequence of life on Earth even without precise year counts. To strengthen relative dating, scientists use index fossils, the remains of species with three key traits. They lived during a relatively short geological period. They evolved quickly, making them easy to distinguish from other species. They were widespread across the globe. These fossils act like timestamps. If the same index fossil is discovered in two rock layers separated by vast distances, scientists can conclude that those layers are of the same relative age, even if the rocks differ in composition. Common index fossils include trilobites, ammonites, and foraminifera. Though it does not provide absolute numbers, relative dating is a powerful tool because it situates fossils within geological and biological context. It enables scientists to correlate rock layers across continents, turning local observations into a worldwide historical framework. This process is not merely about ordering layers of rock. It builds a global timeline that became the essential foundation for the later development of absolute dating methods. Absolute dating, unlocking the nuclear clock. To arrive at precise numbers, scientists turn to absolute dating methods, which rely on the radioactive decay of isotopes found in rocks and minerals. The principle of radiometric dating. At the heart of radiometric dating is the decay of unstable isotopes, known as parent elements, into stable isotopes, known as daughter elements, at a constant, unchanging rate. This rate is measured as a half-life, the amount of time it takes for half of the parent atoms to decay. The key assumption is that once a sample is formed, say when molten rock cools and crystallizes, it becomes a closed system. From that moment forward, no parent or daughter atoms enter or escape. By measuring the ratio of remaining parent isotopes to the daughter isotopes produced, scientists can calculate how much time has passed since the sample formed. Different radiometric techniques are suited for different materials and time ranges. There is no single magic method. Instead, each serves as a specialized tool in a much larger scientific toolkit designed to measure time from thousands to billions of years. Carbon-14, the clock of recent history. Carbon-14 dating is one of the most widely known techniques for measuring the ages of organic remains. Carbon-14 is continuously created in Earth's atmosphere when cosmic rays interact with nitrogen. Plants absorb this isotope during photosynthesis, and animals then acquire it by consuming plants. When an organism dies, carbon exchange stops, and the carbon-14 in its body begins to decay back into nitrogen. Because the half-life of carbon-14 is only about 5,730 years, the method is effective only for samples younger than 50 to 75,000 years. This is why it is never used for dating dinosaur fossils, as these creatures vanished tens of millions of years ago. Potassium-Argon and Argon-Argon, dating rocks and volcanoes. For much older fossils, scientists must date the surrounding rock layers rather than the fossils themselves. One of the most common techniques is Potassium-Argon dating, which measures the decay of potassium-40 into argon-40 with a half-life of about 1.3 billion years. Traditional KR dating, however, faces challenges. Argon, being a noble gas, can leak from mineral crystals if rocks are reheated or altered geologically. Conversely, some rocks can trap extra argon during crystallization, producing excess argon that skews results. To solve this, scientists developed the Argon-Argon method. This refined approach irradiates the sample with neutrons, converting a portion of stable potassium-39 into argon-39. Because the natural ratio of potassium-39 to potassium-40 is nearly constant, measuring argon-40 against argon-39 indirectly reveals the argon-40 to potassium-40 ratio. One of RR dating's greatest strengths is stepwise heating analysis. The sample is heated gradually, and the argon released at each stage is measured separately. If consistent ages appear across multiple steps, forming what is called a plateau, it strongly confirms that the sample has not been contaminated with excess argon or lost argon since formation. This illustrates a deeper truth. Science does not merely invent new methods. It also builds in self-checking mechanisms that enhance reliability. Each refinement strengthens our confidence in the geological timescale, turning invisible nuclear decay into the heartbeat of Earth's history. Uranium-Lead, reaching back to Earth's dawn. For the oldest rocks, those hundreds of millions to billions of years old, the Uranium-Lead (UPB) method is the gold standard. This technique relies on two independent yet simultaneous decay chains. Uranium-238 decays into lead-206 with a half-life of about 4.5 billion years, while uranium-235 decays into lead-207 with a half-life of about 710 million years. The reliability of UPB dating comes from a remarkable mineral, zircon, ZrSiO4. When zircon crystals form in cooling magma, their atomic structure readily accepts uranium atoms, but almost completely rejects lead atoms. This means that when a zircon crystal first forms, it contains virtually no lead. Any lead found within it later must be the result of radioactive decay. Because there are two decay chains working in parallel, scientists gain a built-in cross-check. If both the uranium-238 to lead-206 and uranium-235 to lead-207 clocks produce the same age, it is powerful confirmation that the result is accurate. Using this method, researchers have dated not only Earth's oldest rocks but also ancient meteorites, helping to determine that our planet formed around 4.5 billion years ago. Testing the assumptions. Cross-validation. Skepticism about dating methods often centers on assumptions, but science does not accept those assumptions blindly. It creates mechanisms to test them. This is where cross-validation becomes crucial. No scientist would trust a single method on its own. Instead, they look for agreement across multiple independent techniques. For example, the same layer of rock might be dated using both Potassium-Argon and Uranium-Lead. If the two methods, based on entirely different physical principles, converge on the same result, it provides one of the strongest proofs of accuracy. This practice of testing and retesting across disciplines is what gives geologic time its credibility, turning radioactive decay into a trustworthy timeline of Earth's deep past. The role of paleomagnetism. Beyond radiometric dating, scientists use another powerful independent tool, paleomagnetism. Earth has its own magnetic field, and throughout millions of years, that field has flipped its polarity many times. When lava erupts and cools, the iron-bearing minerals inside align themselves with Earth's magnetic field at that precise moment, locking that orientation forever into the rock. Over decades, geologists have built a detailed geomagnetic polarity timescale by combining paleomagnetic data with radiometric dating. If a fossil is found within a rock layer whose ancient magnetic signature is known, that fossil's age gains independent confirmation, evidence that does not rely on radioactive decay at all. This shows that the age of a fossil is never just a number. It is a key to unlocking a vanished world. Those numbers allow scientists to place organisms on the geologic timeline and reconstruct the environment in which they lived. Ardipithecus ramidus, 4.4 million years ago. In 1994, scientists uncovered an extraordinary fossil skeleton belonging to one of humanity's earliest known ancestors, Ardipithecus ramidus, nicknamed Ardi. Found in Ethiopia's Middle Awash Valley, Ardi's discovery fundamentally changed our understanding of human evolution. The site contained volcanic tuff layers, perfect for radiometric testing. Using the Argon-Argon method, researchers dated both the ash layers above and below the fossil to about 4.4 million years. That precise age overturned the long-held theory that human ancestors first evolved in open savannas. Instead, Ardi's world was one of shaded woodlands, a revelation that reshaped evolutionary science. The Laetoli Footprints, 3.6 million years ago. Few discoveries capture the imagination like the fossilized footprints at Laetoli, Tanzania, attributed to Australopithecus afarensis. Their preservation was a stroke of geologic luck. First, a nearby volcano blanketed the ground with a layer of fine ash. Then a light rain transformed that ash into a cement-like mud. A pair of hominins walked across it, leaving behind tracks unmistakably bipedal. Soon after, another eruption covered the surface with fresh ash, sealing the footprints beneath a protective layer. Argon-Argon dating placed the footprints at about 3.6 million years old, our earliest and most compelling evidence of habitual upright walking, a behavioral milestone preserved by the unlikely meeting of geology and biology. Other fossil timelines. Reconstructing vanished ecosystems, Arthropleura, 326 million years ago. Fossils of this giant millipede, dated to the Carboniferous period, reveal a world that existed long before the dinosaurs. During this time, oxygen levels in the atmosphere were far higher than they are today. That abundance of oxygen allowed insects and other invertebrates to grow to astonishing sizes, reaching dimensions never again seen in Earth's history. Cameroceras, between 450 and 470 million years ago, this enormous cephalopod reigned over the Ordovician seas. Dating its remains places it among the earliest apex predators of the ancient oceans, where it shared its domain with trilobites and brachiopods. Mazon Creek, 309 million years ago. This world-famous fossil site in Illinois dates back to the Pennsylvanian period, capturing the remnants of a lush tropical swamp ecosystem. Because of a rare type of sedimentation, fossils here are preserved inside siderite nodules, with extraordinary detail, sometimes even retaining traces of soft tissues. Mazon Creek offers one of the most complete and vivid windows into ancient life ever discovered. Dating a fossil is never a simple calculation. It is a painstaking, rigorous scientific process. It blends multiple methods, from arranging rock layers in relative order to using the precision of radioactive clocks, and finally cross-checking results with independent evidence like paleomagnetism. Each method carries its own assumptions and limitations, but the very essence of science lies in continually developing new techniques to test, refine, and overcome those limits. When scientists announce the age of a fossil, that number is not plucked from thin air. It is the outcome of careful comparison, supported by agreement across multiple independent lines of evidence. Every date is a piece of the puzzle, helping us reconstruct, with remarkable detail and accuracy, the grand story of life and evolution on Earth. So now, after exploring the complexity and sophistication of these methods, do you believe the evidence is strong enough to trust? Or do you think we have only glimpsed a small corner of a much greater picture? Share your perspective in the comments and let us know what mysteries you'd like us to uncover next. And if you want to dive deeper into Earth's secrets and the incredible saga of prehistoric life, don't forget to subscribe so you won't miss the exciting stories we're bringing your way.